We're going to be covering section 2.6 in your textbook today, and we're going to be taking a couple of word problems that have to do with percentages and how to translate those words into mathematical representations and solve. So I feel like as we proceed into the higher level divisions of mathematics, word problems become the way to apply the mathematics that you've learned. And hopefully a couple of the problems that we work through in the book give you some indication of the kind of things that mathematics is actually useful for. So by way of sort of teasing, so if you're a shopaholic, we're going to be talking about discounts and markups today. If you're like me and you're a foodie, we're going to be talking about peppers, hot peppers, which are some of my favorite things to eat. And we're going to be doing some mixture problems. I'm a Tromix guy, so we're going to do a Tromix problem today. So I like to tackle these problems because they are real-world problems. It's where we get all of these funny symbols from. The problems that we did in 10,000 years ago didn't have the symbols x plus y equals some constant. They were, they were word problems. They were actually sentences that people had to follow along and interpret. So I feel like if we treat math like a language, as it has been treated for thousands of years, and we approach these problems linguistically and we develop the translation skills that we need, then we can kind of get an idea of being more okay with word problems and what's actually going on, and the fear will evaporate. That's my ultimate goal. All right, so let's see if we get there. Hopefully we can. The first thing that I want to do is sort of I want to make basic translations. So I say, if I were to ask you, take any number and add 3. And I should even write that as the word 3, right? Could you translate this English sentence into a mathematical representation? The answer is yes? Question mark, maybe? This translates to, we're going to let x, the letter x represent any number, right? So that's the first sort of translation that we do. And we're going to add, there's our clue. We're going to use the symbol for add, which is the plus symbol. I know this seems a little dull, but we're going to build up to some more complex things here. And add 3, we have a symbol for 3. So the way that we would write this as an expression is x plus 3. This is any number that we take and then add 3 to it. Okay? So these are the kinds of things that you'll need to get comfortable doing. If I were to say, what number is 85% of 63? Question mark. How would we translate this sentence into a mathematical equation? Again, with any number or what number, we're going to let x represent the number. We don't know what it is yet. Anytime you see, or I should say most every time you see the verb is, that's your clue that we're using an equal sign. So is, well, I should write the symbol here. The equal sign represents is. 85%, this percent symbol means that we have to turn whatever number we have into a decimal. Because we talk about getting 100% of something, it means we're talking about getting the complete, all of it, right? So when we put this percentage sign of something, what we really are corresponding it to is one whole object, right? There's no part of the object that is left out in 100%. So if you get 100% of your daily vitamin C, you got all of it, right? If you get 50% of your vitamin D, maybe go grab some orange juice, right? Or if it's vitamin D, go out and play in the sun. Anyway, so we got 85%. We need to convert this into a decimal. So the way to do this is to use the fact that if I have 100 out of 100 as a fraction or as a ratio, I have one whole thing, right? So if I have 100% of something, or if I have 100 out of 100 of it, I have a whole thing. So if I have 85 out of 100, I have 85% of it, okay? And then we could also represent this as a decimal, 0.85. All of these are correct equalities. They represent the same thing, all right? So when we're making these translations, this is where math translation becomes a kind of art, you know, whatever is easier for you to deal with. Clearly, the percentage sign is a little clunky to work with. So do you like to work in fractions? Great. Use fractions. If you like to work in decimals, great. Work in decimals. It's up to you. I'm going to use a fraction. I'm going to use a ratio. So I'm going to say 85% is going to be my 85 out of 100. Okay. So I've translated this part, I've translated this part, translated this part of 63. Now this might be the tricky part. Anytime that you see a percent of, we are dealing with the product of something, all right? I want to know, because if I have 85 out of 100 parts, and I multiply that by the value of that part. Let's say that I have 85 out of 100 cents. And I say, well, I want to know how many cents or how many dollars do I have, right? If this represents the value of $1, I still don't have a whole dollar. I only have 85% of $1, okay? And I know it's a little tricky, but anytime that you see the word of, we are, I should say most times that we see the word of, we are dealing with either some product or some division. And in this case, it's going to be a product, because we have a percent of a product, a percent of a value. So the word of will represent, and I'll use the dot to represent the multiplication. This is going to be congruent with of. And then 63 is our value. That's the thing that we're going to be multiplying this fraction by. So the way to translate this, x equals 85 over 100 times 63. We can drop the question mark because we're not asking a question anymore, we're answering it. Okay? And now when we make this translation from English into mathematics, we have all the tools that at our disposal to solve this for x. This is a very easy, relatively easy calculation to make. So let's go ahead and solve. So let's see. The first thing that I want to do is I want to eliminate my fractions. So I will multiply both sides by 100, or I should say I'll multiply everything by 100. So I get 100x equals 85 times 6,300. And then let's see. I don't have my calculator here, so I'm going to have to do some quick work here. So dividing through by, or multiplying both sides by 100, I get 100x on the left-hand side, and I get 5355 on the other side. Dividing by 100, I get x equals 53.55. And that is the number that is 85% of 63. So we've taken a word problem, admittedly a very easy word problem to do, or a simple word problem with not a whole lot going on. And the most important thing that we've done is we've translated from English to mathematics. And once we got it into mathematics, we could solve for the thing we didn't know. All right? And this is how it will work with all of your word problems. You will kind of have to make your first step be, well, how do I translate from English to mathematics? So let's take another example. Let's take some examples from shopping. Okay, so if you're out buying school clothes or whatever, I don't know, computers, whatever you need for school, and maybe you walk into the Apple store and you see a MacBook Pro that's discounted by 30%. Like Apple would ever do that, but you know, indulge my fantasy here. Let's see. Let's say that we've got a MacBook Pro whose original price, so the original price of a MacBook Pro is, man, I'm being generous, $2,000. Okay? We walk in the store, and the MacBook Pro is discounted by 30%. What is the new price of the MacBook Pro? The MacBook Pro. Question mark. Okay, same sort of technique that we used for our first percentage problem, only this time we've made it a little bit more challenging. So we have an original price. We have a discount that's given, a percent discount that's given, and we're asked to figure out the new price. Okay? So the first translations that we need to do is we need to set aside the things that are given. So I would say original price is, which means equals, $2,000. And let's see, the discount equals 30%. And this time I'm going to use my conversion into decimal. So that is 0.30 for my discount. And then I want to know what is the new price. So what, and I could say what number here, which is my clue. What the thing that I'm looking for? What is the thing that I'm looking for? Well, it's the thing I don't know, so I'm going to call it X, or I'm going to call it Y. Why don't I call it P for price? Just to mix up the variable. So P will represent the new price. Okay? So what I'm asking, this is the thing that I'm trying to figure out. So this is the translation I need to make. What I need to say is what number is the discounted price of my original price. So what number, P, is equal to 30%, this is 30%, 30 of, right? What is the new price of the MacBook Pro? 30% of the original price, which was $2,000. So 30% of $2,000, our original price, is $600. Now, the way that I've set it up is that I've let P equal new price. Well, if you forked over $600 and expected to walk out of the store with that MacBook Pro, you wouldn't make it. Because in this case, P represents the value of the discount. We wanted to know what the new price of the MacBook Pro, but what our setup gave us is the percent of the original price, the percent that is knocked off. So we kind of have to go back to a thing that isn't really discussed about when we're working with problems. And part of the thing that makes word problems so tricky is that embedded in word problems are these abstract relationships that you're kind of expected to know. Like the idea that a discount is a value that you take away from something original. So whenever you're confronting word problems, what you need to do is you need to collect the information that you're given. But the second step is that you need to ask yourself, is there something they're not telling me that they're expecting me to know already? So let's see, and I call this what should I infer from the problem? Infer is just a fancy word that means what should I read into? Or what should I assume that the problem is telling me that it isn't directly stating? Okay? So for example, the context of this word problem suggests that we need to know how to compute new price based off of discount. So we have to talk about abstractly how to do that. So if I'm discounting something, that means I'm taking part of the price away from the original price. So the formula that we use is that the new price equals the old price minus the discount. This seems to make sense, right? When you walk into a store and you see something that's discounted, you don't expect to pay more for it, you expect to pay less. So if you have an old price and you subtract the discount, you should get the new price, okay? Well, we have computed the value of our discount and we have our original price. So now we can create this relationship and solve for the thing that we need to find out. So we'll let n represent new price, and we have to build another mathematical relationship. We have n equals the old price, well, that's 2,000, minus the discount that we computed. So this is 600. And the new price, once we do this simple subtraction, is $1,400. Okay? So we had to collect the information. And then the second thing that we had to do, and as you grow into higher level math classes, your instructors will expect you to know this stuff. And the way that they'll do this, some of them will actually present abstract concepts to you. For example, when you get into 126, they'll start talking about revenue. Well, how do we talk about revenue? Revenue is, what is it, price times sales, or sales times quantity, or there'll be some abstract relationship like revenue equals the cost of your product, or I should say the price of your product, how much you charge per unit times the number of sales, so the quantity of sales that you make. And you'll see these sort of setups where in class you'll be like, oh yeah, this is sort of the way that we think about revenue and price. And then you'll be asked to build a function that's just a revenue function based on price. So, and it'll be expected that you know to use this abstract relationship and turn it into some form of mathematical representation. Like this is an abstract representation of things. New price is computed by taking the old price and subtracting the discount. That's the abstract version of that. And then we had to use what information we had in our word problem and turn it into a mathematical expression and solve for our unknown variable. That's how these problems will go nearly 100% of the time. Okay? So I was going to do a markup problem, which is just sort of a discount problem in reverse. Instead, I'll just leave you with the abstract idea of what a markup is. So again, markups are things that we don't want to see. Discounts are things that we want to see. So for a discount, the formula is new price equals old price minus the discount. And we say that the discount is always a percent of the original cost, or the original price. All right. For a markup, we use the same kind of ideas, only we make one important distinction. Discount, or I should say markup, is still a percentage of the original price. And you guys are probably already there with me. But we're marking it up. We're adding it on. So instead of subtracting it, we're going to be adding it to. So the new price of a markup equals the old price plus our markup. So instead of working through another, there are plenty of examples in your book that deal with discount and markups. And I think that those are extremely, they're particularly relevant problems to work through because you'll be shopping a lot in your future. Particularly here in college, you'll be buying textbooks. This is a thing, a big thing. You very rarely see this. You see a lot of this. So sorry to spoil college for you. There it is. But I want to use discounts and markups to talk about ways to think about problems that deal with increases and decreases. Okay. So the one that I want to bring to you right now is a problem that I discovered today, and it blew my mind because I'm a fan of hot, spicy foods. And it talks about a unit of measurement, a very specific unit of measurement called the Scoville unit, or we could say Scovilles. And it is the unit of measurement that measures the hotness of a pepper for hot peppers. Usually, I was blown away that there was some quantity that we used to measure pepper hotness. I just wipe my face. That's how I do it. So what we're going to do is we're going to look at a problem in your textbook here, following along. It's a problem from section 2.6, and it is problem 57. And it says that for a while, the red Savina pepper I don't think I've ever had one of these, had a Scoville unit rating of 577,000 Scoville units. Okay? Just to give you some context, like a yellow pepper that you would buy at a grocery store has exactly 0 Scoville units, okay? I think a habanero is in the 85,000 range, okay? So we're dealing with hot pepper, okay? Now the question says that up until recently, this was the reigning champion, but then we discovered a new pepper called the Naga, I don't even think I'm saying this right, Jolokia pepper, okay? And this pepper is 48% hotter than the red Savina. So we're going to figure out how many Scoville units it rates on the scale, okay? So we're going to take this word problem, and I've sort of broken it up into the parts already, but if you're reading along with the word problem or you stop and you go find it, basically I've done the first step for you. I've collected the information. And I want to know, what, or I should say, how many Scoville units is the Naga Jolokia pepper? So I've taken the first step and collected our information. I know that 577,000 Scoville units is our original hotness. And I know that we have a pepper that is 48% hotter, okay? So now I just have to go to step 2 and remember that there are things that I'm expected to know that aren't written down. Like, what does it mean when something increases by 1% or decreases by 1%? So I'll share that with you. When you have an increase by percent, what you want to do is you want to calculate what that increase is, like the raw value of what that increase is. So similar to our markup, since we're dealing with increase, let's use the markup relationship. So we'll say increase equals, I should say the value of the increase is equal to the percentage times the original. Okay, the original value. And then we'll say that the new value, similar to the markup, will equal the original value plus the increase. Okay? So we have 577,000 is the original value. So we'll plug that in over here, 577,000. And then we'll have the increase, which we don't know. So we'll call it V. We'll let V equal the increase. And it's a percentage. Well, what's the percentage that we have? It's 48%. But remember what we do with percentages. We have to turn them into either ratios or decimals. Okay? And I'll use a ratio, 4,800. Okay? And just like we did in the first example, we'll solve for V. So let's see if I can do this time. After we take our break and do our calculations, we come back with 276,960. This is not our new value. This is just the value of our increase. So we have to go back and compute our new value, which means we take the original value and we add this thing together. So our new, so the how many the number that we're looking for, right? How many Scoville units are we looking for? Is computed by taking the original value, 577,000 plus 276,960. That's 854,000, something like that. It's a pretty big number. That's hot. So, you know, if you like hot stuff, good luck with that. Okay? So we've covered percentage problems, we've covered discount and market problems. The last thing that we should probably talk about is mixture problems. Okay? And we should talk about them because the book covers it, so we're going to do it. We're going to use the same steps that we do. We're going to collect given information, we're going to make our basic translations, and then we're going to ask ourselves if is there something that we need to infer from this problem. Something that's not given to us, but something that our instructor expects that we know. All right? So I love trail mix. I like to eat trail mix, partly because it has a lot of good things in there and some bad things like M&Ms. That's right. So what we're going to do is we're going to make our own trail mix, and we're going to open up a business and we're going to sell it. All right, and we're going to find the right price that we need to charge in order to make back what it costs us per pound, so that we don't go broke. All right. So let's see. Let's say that it costs us $2 per pound for peanuts. Okay. Not the preferred nut in my trail mix, but it's cheap. If I was doing almonds, it wouldn't be $2. Very expensive. So let's say that it costs us $4 per pound for M&Ms, right? The bad part of the trail mix. And let's say that it costs us $3 per pound for raisins. Okay? Classic, basic trail mix. Now we want to know, and we know that we're going to mix all these ingredients together, and we're going to assume that we're going to sell this by the pound, and we want to know how much should we charge per pound so that we don't lose money. We just want to break even. Okay? What's the minimum that we can charge so that we don't lose money? We're not paying anybody, we're just covering our costs. All right? So this is charity trail mix, so that we don't lose money. Okay? Well, we know if we can collect our information in sort of a visual way, we'll have, let's say that this box represents one pound of our peanuts, so our peanuts, and that this represents 1 pound of our M&Ms, and this represents 1 pound of our raisins. We know that every time that we have a quantity of 1 pound, it costs us $2. Okay? And we know that when we buy our M&Ms, it costs us $4. I don't know why they're so expensive, but they are. And then it costs us $3 per pound for our raisins. We have two things going on here. We have quantity and we have cost. Okay? So we like a good way to do this. It's not the way that you can do it. It's a way to do it. Is to build a table, okay, where you have the objects that are given and you're setting them up and organizing them in a way that makes sense for you to translate from English to mathematics. So let's say we've got our peanuts, we've got our M&Ms, we've got our raisins, and we'll let this row represent the cost, and we'll let this row represent the pounds, right? So pounds. So for peanuts, it's going to be $2 and it's 1 pound. And then we've got $4 for 1 pound, and then we have $3 for 1 pound. This is starting to look like ratios, isn't it? For every 1 pound, we have $2, right? The ratio of quantity to price. This is an important concept, all right? What I'm doing is I'm adding these ratios together, aren't I? I'm taking $2 for every 1 pound plus $4 for every 1 pound and $3 for every pound of raisins, and I'm adding them together. Well, what do I do with fractions? I have to add them up, don't I? But when you see abstract relationships like this, like you can rewrite this as the number 2, right? When you do that, in this case, you're making a big mistake. The reason is that we're not talking about the same thing. These aren't fractions anymore. These are ratios. These are comparisons of different objects. So I have dollars to pounds. So I have to keep both my things together. So I add up my 2, my 4, and my 3, and I get $10. But I'm adding my pounds up. I have $9. And then when I add my pounds up together, I get 3 pounds. Okay? And I know this is sort of like we've been teaching you to work abstractly with ratios, but this is a deliberate thing that you need to understand, is that sometimes a ratio is a comparison of 2 different objects. And when it is, you can't treat it like a fraction. You have to treat it like a ratio, which means you keep everything grouped together. So what I'm saying is that for every 3 pounds of trail mix, it cost me $9, right? But what do I want to know? I want to know how much I should charge per pound, okay? Well, where are my pounds? If I have 3 pounds that cost $9, and I want to know how many, so let's say I have $9 for every 3 pounds, what number, right, do I have to charge for 1 pound? Right, for 1 pound. You may have seen this sort of relationship before. This is simple. We just cross multiply. So here we're going to go $9 for times 1 pound will equal 3 pounds times X. And when I get X all by itself, it means that I divide both sides by 3 pounds. And when I do, not only do my numbers reduce, but also my units cancel. Right? Pounds cancels with pounds. Pounds cancels with pounds. I'm just left with $9 divided by 3 is just $3. Okay? And that's the minimum price that I should charge in order to break even. So what we've done is we've taken a word problem and we've broken it into its concepts, right? Visually, we set up a table, and that table gave us a comparison. And I like this approach because we get back to the idea of what a ratio is, a comparison of two separate things. When it's a comparison of two separate things, we have to keep those separate things separate. Otherwise, the ratio falls apart. But it makes it a little bit more intuitive, I think, when we're adding these things up together and keeping our units separate. It tells the story of what we're actually doing. You can actually see, oh yeah, $2 per pound, $4 per pound, $3 per pound gives me $9 for every 3 pounds, not every 1 pound, but every 3 pounds. And then solving for the number. What number do we need to charge? And setting up our equality. When I have $9 for every 3 pounds, what number do I have for every 1 pound? And then solving for our unknown variable. Okay? And I promise you, the more you work with word problems, the more comfortable you'll get with them. And the more excited I think you'll get about mathematics, because so much of mathematics is built in the actual solving of everyday problems like this. Okay? Good luck.